rather cryptic comment that in the study of black holes, predicted by this 100-year-old theory of space and time, we're now being forced to reassess our understanding of space and time themselves. And I'd like to go on that journey, follow that road now. So I've gone back, this is the map of the black hole again. I've now drawn it in crayon, so it's less threatening. But so this is the map that we saw before, the Penrose diagram. The grey diamond is the exterior, infinite, eternal exterior universe. The golden region is the interior of the black hole, and the red wavy line is the singularity. Now, in 1935, Einstein and a colleague of his, Rosen, published a paper in which they discovered that this is not all there is to the map, which is a strange thing to say. It's an infinite eternal universe and a black hole. The problem, which is easier to see actually in a Penrose diagram, and they didn't have them at the time, is this line here, which is really an event horizon. It's not infinity. It's not the end of time up here. It's as if it seems like there should be something else in this region. In the map, remember this is just hiding in that mathematics that Schwarzschild discovered all those years ago in 1916. Turns out that there is. If you draw the full map, so-called maximally extended Schwarzschild space-time, then you get this. So what is this? Right, because now there's another universe, another one. Two infinite eternal universes. And then there's something that looks like an upside-down black hole. What's that? Well, remember, this is still a Penrose diagram. And so light rays travel upwards into the future, 45 degrees in straight lines. So that means that anything in here inexorably comes out into one or other of the universes. So this is a white hole. In a sense, the opposite of a black hole. And that's that region in between the two universes where they seem to touch inside the black hole. So what is that? Well, I took Schwarzschild's equation and put it into a program called Mathematica, and then added another space dimension, and asked it to draw a graph. So this is now not an artist's impression. It is actually a graph of Schwarzschild's equation in that region. This is known as an Einstein-Rosen bridge, or a wormhole. So those things that we're all familiar with in science fiction, wormholes that connect distant regions of the universe, or perhaps other universes together, actually exist in Einstein's theory of gravity, in this geometry. And this is just the beginning to the richness and beauty of Einstein's theory. And black hole, particularly around the event horizon of the black hole. In quantum theory, empty space is not empty. If you zoom in into the vacuum of space, imagine with a microscope and slow time down, you could picture the situation as space being filled with particles coming into and out of existence all the time in pairs, and these pairs are entangled. So the vacuum of space in quantum theory is heavily entangled. It's the structure of the vacuum itself. That's important. It's sometimes been described as the glue that holds space together. Now what Stephen Hawking did is he thought about what happens to that vacuum around the event horizon of a black hole. So imagine, you can picture the idea where these particles, the entangled particles, one of them's on the inside of the horizon, and one of them's on the outside. They're entangled with each other. But now they're separated, and we know what can happen to the one on the inside. It goes to the end of time. It's not coming out in the black hole. The upshot of that is that the other one can escape. It's kind of made real, and it can escape into the universe. This is called Hawking radiation. This is what's causing the black hole to glow. It's the black hole kind of disrupting the structure of the vacuum itself. So black holes, well, they have a temperature. So important was that discovery that if you go to Westminster Abbey and you look on the floor of the Abbey, on Stephen's memorial stone, then literally chiselled in stone on the floor of the Abbey is that equation, T equals T, the temperature of a black hole. Why? Why is it so important that someone decided to chisel it in stone on the floor of Westminster Abbey? The reason is that this discovery set up a fundamental clash of principle in physics, in particular to quantum theory and relativism, the two foundations of 20th century physics. And that clash is called the black hole information paradox. And here's the problem. The problem is this. So I've said this thing is glowing. Stephen Hawking discovered it as a temperature. It emits things. And over huge time scales, much longer than the current age of the universe, for big black holes, these things shrink and shrink because they're emitting energy, losing energy, and ultimately they shrink away. They go. One day, the black hole will be gone. The question is, what happened to the entanglement? Remember, these particles are being plucked out of the quantum vacuum. So they're entangled. You can think of the radiation being entangled with the black hole. The black hole goes. So the question is, what are these entangled with now? It's like the entanglement has been destroyed. The problem is, there's information in entanglement. Right? Remember I said with the quantum coins, this one comes up heads, that one comes up tails. So somewhere in this whole thing, there's information. It's kind of distributed. It's a bit weird, but it's stored there. If this thing disappears and the entanglement is destroyed, then the information has gone. So Stephen's initial calculation suggested that these things erase information from the universe. That's not allowed. Nothing does that. This is called determinism. It's fundamental to all of physics. It's the idea that if you know everything about something, some system, at some point in time, then in principle, not in practice, but in principle, you can calculate exactly what it's going to do in the future and exactly what it was doing in the past. But if you've got things sitting at the sites of collapsed stars or the centres of galaxies that erase information from the universe, then determinism is dead. And the foundations of physics crumble away. So that's why there's a fundamental problem with black holes radiating, the black hole information paradox. Now, as I said, people worked on this then for 50 years. It's a tremendously interesting problem. All clashes of principle in physics are interesting. And it was solved, really, the beginnings of the solution, as far as most physicists are concerned, appeared in 2019 in a couple of papers and then subsequent work. So what I want to do is I want to try to give you a flavour of what that solution is, because it is fascinating and it is